Hi there! Inductors are electric devices capable of storing energy in the form of a magnetic field. In their basic form, inductors are simply made with a loop of wire or with a coil. They can be arranged in air or on a ferromagnetic core. Today we will take a peek at the theory behind them, and then we will concentrate on verifying experimentally how they work. But before diving into the details, please take a moment to subscribe to this channel and click on the bell icon to receive notifications when new videos are published. The subscription will also help in making this channel grow and serve you better. Let's begin. Inductance is the property of opposing changes on the electrical current flowing through a conductor. Any conductor has an inductance, but depending on its shape and the vicinity to certain materials, the inductance can be very small or very high. A single wire has an inductance. If we take the wire and we shape it as a loop, the inductance increases. If we make several loops with the same wire, which we call a coil, like this, the inductance becomes even higher, and if we create a coil around a piece of iron, the inductance becomes much higher. Those conductors that are shaped and built to provide a relatively high value of inductance are called inductors, like this one or this one. But how do we measure the inductance? The inductance has the property of opposing at changes in current. So let's consider an inductor represented with this symbol, and a voltage applied to it, which we represent with this battery here. Because the inductor is made usually of good conducting material, like copper for example, a considerable amount of current will flow through the inductor itself, causing eventually to burn the generator or the inductor if the wire is thin. So let's put a resistor in series to limit the amount of current that goes through the inductor to a reasonable value. And let's put it this way, in series with the inductor L. Now let's suddenly change the voltage applied to the circuit. To do so we can use a switch like this. So we basically close the switch at the instant t equals t0. Let's see what happened to the system. And let's draw a diagram of the voltage and the current between this point and this point. Between these 2 points the voltage is the same as the generator, so basically at the instant t0 the voltage will do this. Normally the current would do the same, but in this particular case, because of the inductor, the current will not change instantaneously to its new value, but it will reach that value in a certain amount of time. Let's say we'll do that at this time here. So at this time we will reach the maximum value. The ratio between the change in current and the time in which that happened is proportional to the voltage applied to the circuit. And the proportional constant is called inductance, which we indicate with the letter L. So this is the formula that allows us to eventually calculate the inductance L of an inductor. Now this formula also tells us that when we change the value of the voltage, for example, let's say initially we had a V0, and instead we replace this battery with a different one, which is 2V0. Then the current will increase also at the new value, but the time where this happens is exactly the same. And I can anticipate right now that it's gonna do something like this way or this way. But the time basically depends only on the constant L, does not depend on the amount of voltage and on the amount of current. So the inductance is basically the constant that provides the value of the voltage to change to obtain a certain amount of current change in a certain amount of time. Again, it is represented with the letter L, and it is measured in what we call Henry, which is a measurement unit which name comes from Joseph Henry, which was the scientist that discovered the phenomenon of inductance. But why the current does not change at the same pace as the voltage? The reason behind that is the magnetic field. Now, I know you're saying, what has anything to do to the magnetic field with a current in a wire? Well, it has everything to do. In fact, we can see experimentally that when a current flows into a wire, any kind of wire, then around the wire a magnetic field is generated. And these magnetic fields is capable of interacting with a magnet. For example, if we take a compass and we put it in proximity of the wire and there is current flowing into it, the compass needle will be affected by the magnetic fields generated by the current in the wire. Let's see how this happens. So let's use this compass for our experiment. Right now the needle points toward north. Now I'm gonna use this cable here, which is right now traversed by about 0.5 amps current, and we move it on top of the needle. Look what happened. See, the needle moves. Can you see it? So this basically demonstrates that current generates a magnetic field. So back to the original question, the current does not change instantaneously when the voltage changes on the wire, because the voltage has to provide first enough energy to modify the magnetic field. Only when the magnetic field is modified, the current can change. So basically that explains why we see this kind of behavior between the voltage applied on the inductor and the current that flows through it. All this happens a little bit at a time. First, at the moment the voltage changes, the magnetic field changes a little and the current changes a little as well. Then the magnetic field changes a little more and the current changes again, and again, and again, and again, until we reach the time where the current has reached its maximum value and so does the magnetic field. At that point, the current does not increase anymore, and this point is when basically the current is limited only by the resistor in the circuit that we saw before. So if this is V and this is R, the current at the end over here will have a value I0 equals V over R. Another interesting thing is why the change in the magnetic field causes the current to change. Every time the magnetic field changes a certain amount, it increases a voltage of its own at the connectors of the inductors. So let's draw the circuit again. We have a switch, we have the resistor, and we have the inductor here. Let's call this E, this R, this L. And let's measure the voltage right over here. Initially, when the switch is open, the voltage, of course, is 0. But when we close the switch, then the generator E will try to make the current flow across the circuit. At that point, the inductor will start charging its magnetic field, but in doing so, it will generate a voltage of its own over here, with plus on this side and minus on this. And this voltage will be exactly equal to the E over here. So you can see that the difference of potential across R becomes 0 at that point, and so there is no current. That's why at the very beginning, when the switch is closed, there is no current. But then the inductor starts charging, and while it charges and accumulates magnetic fields around it, this voltage across the inductor will start reducing a little bit at a time, and so a difference of potential will be created around R, which will keep increasing over time, and so the current across this series will start increasing as well. Then at one point, the current will be equal to the maximum possible value, which is dictated by the voltage at the generator, and at that point we will reach an equilibrium for which there will be no more additional magnetic field across the inductor L, and the current will not increase anymore. At the same time, there will be 0 volts again across the inductor L. The voltage across the inductor L is called counter electromotive force, or back electromotive force, or simply back EMF. Basically, this back voltage is the one that opposes the voltage applied to the circuit by the generator, and then will cause the current limitation, and the current won't be able to flow across the circuit right away when the switch is closed. So in black we have the current that flows to the circuit. If we want to represent the V in this same diagram, we could do it this way. And we can see that the current does not reach its maximum value until after a certain amount of time after the voltage has done it. So when the current takes some time to reach its correct value with respect to the voltage, we say that the current lags the voltage. We can easily see how this happens with a simple example. So let's assume we still have the same circuit, this time with a sine wave generator, the resistor R, and the inductor L. So the sine wave applied between these 2 points, so between the series of the R and L, let's say follows this shape. Now the current that flows into the circuit will follow also that shape, but will not follow it right away, because the inductance, or the inductor L, will prevent that from happening, because it will create a back EMF over here that will prevent the current to flow right away until at least the magnetic field is maximum. So what happens really is this, that the current will start flowing after a certain amount of time that the voltage has started. So let's say it does it this way, comparing the various points. So the current will do something like this. So basically the current will lag behind the voltage over an amount of time that depends on the value of the R and depends on the value of the L. In general, if there was no R but only the generator and the inductor, this difference will be exactly 1/4 of the wavelength, or basically 90 degrees. So we say in general that for the inductors, the current lags 90 degrees behind the voltage. We will see this later on with a simple experiment here in the lab. Let's review these concepts in practice now. Later in this video we will also learn how to deal with inductors in series and in parallel. In the meantime, in this lab, we will use an inductor of 10 mH, a resistor box to select the most appropriate resistance value to observe the phenomenon, and a generator that will provide the voltage to power the circuit, and finally also an oscilloscope to watch what happens. Let's start with a simple circuit to measure the back EMF generated by the inductor when we change the voltage powering the circuit. The circuit will have the generator over here, in series with a resistor and an inductor. The oscilloscope will be connected directly to the leads of the inductor, so right in this point and this one, so we can measure directly the voltage at the inductor. Another channel of the oscilloscope will also be connected to the generator on this side, this point here and this point here. So we can see what is the voltage provided by the generator, which will be just like a square wave, and we can compare the input voltage and the output generated by the inductor. And here is the circuit. The inductor is the black cylinder on the little breadboard, the resistor is made out of the resistor box, channel 2 of the oscilloscope, which is the blue one, goes up there on the oscilloscope, and channel 1 is connected directly from the generator to the oscilloscope so we can watch both input voltage and voltage at the inductor at the same time, where the voltage at the inductor, as we said, is the back EMF. So let's take a look at what happens here at the oscilloscope. Let me zoom in so you can see better. So here you can see that as soon as the input voltage changes, a back EMF is created by the inductor to prevent the current from changing. At the same time, the energy provided by the generator is used to increase the magnetic fields around the inductor, and while the magnetic field increases, the back EMF decreases, until once the new intensity of the magnetic field is reached, the maximum intensity, the back EMF goes to zero. Now we can see the same effect when we remove the input voltage. Let's do it this way, so we can see the other end of the shape of the wave. Here we go. Let me raise this a little bit so we can see it better. In this case, the inductor generates a back EMF that will try to sustain the current that was flowing inside of it, but doing so dissipates the energy that was stored in the magnetic fields, so the back EMF starts going to zero from the negative value until the magnetic field is gone. At that point there is no more back EMF and there is no current in the circuit. Let's now see what happens to the current inside the conductor. To do so, we have to change the circuit a little bit. Since the oscilloscope can only measure voltages and not currents, we need a way to convert the current going through the inductor in a voltage that we can measure through the oscilloscope. And we do this using a resistor through which the same current of the inductor flows through. So basically in this case, we can connect the oscilloscope right over here. The oscilloscope will read the voltage across the resistor, but that voltage is proportional to the current that flows into the inductor, so indirectly the oscilloscope will show us how the current flows inside the inductor. And again, we will put also another channel of the oscilloscope connected directly to the generator, so we can see at the same time the voltage provided by the generator and the current that flows into the inductor, and we can compare them directly. And here is a new circuit. The inductor is still on the breadboard and it's connected still in series with the resistor provided by the resistor box. The channel 2 of the oscilloscope this time is connected in parallel with the resistor box, while channel 1, as it was before, is still connected to the generator directly. This way we can compare the two signals. Let's take a look at them. So this is the case where the voltage is suddenly increased, like here. Because of the back EMF that we saw in the previous case, the current initially does not flow, but then a little bit at a time, while the magnetic field reaches its maximum, the EMF decreases and the current can increase finally, following the shape of this curve. So now let's go to the other case where we remove the voltage suddenly, which is this one. This time the magnetic field is there on the inductor and needs to go away, so it provides a back EMF that sustains the current when the voltage goes to zero and dissipates the energy that was stored in the magnetic field a little bit at a time. So the energy goes away, and while it goes away the back EMF reduces, and consequently also the current becomes smaller and smaller until it goes to zero when there is no more magnetic field stored in the inductor. Let's do one more test now. This time we will try to visualize the lagging of the current to the voltage. We will try to see if it is actually 90 degrees. The circuit to do so is exactly the same as the previous test. In fact, we want to measure again the current flowing in the inductor, so we need the channel 2 of the oscilloscope connected in parallel to the resistor. What changes is the input voltage from the generator, that now is a sine wave, as you can see here. So let's see what the oscilloscope shows us now. Here it is. So you can see how the voltage in yellow and the current in blue do not change at the same time. Let me superimpose the two pictures so you can see better what's going on. There we go. So there it is. You can see that the distance between the two peaks, or better, when there is a peak in the current the voltage is zero, and vice versa, when there is a peak in the voltage the current is zero. This means that the two peaks are distant exactly 90 degrees, which is the time between the zero value and the peak of the input voltage. And because the current comes after the voltage, we say that it lags behind. When we use inductors in actual electronic circuits, it happens sometimes that we have to put them in series, like this, or in parallel, like this. I don't want to get too much into calculations. Since these calculations involve quantities that change over time, it requires the usage of integrals, and I don't want to go over there right now. I will just say that the inductors in the presence of alternate current behave like resistors in the presence of the direct current. So basically, when we put inductors in series, their inductance L1, L2 is added, and so the equivalent inductance of the series, as if this was a single inductor, will be equal to the sum of the two inductances. Likewise, inductors in parallel follow the same equations as resistors in parallel. So basically, the reciprocal of the equivalent inductance is equal to the sum of the reciprocals of each inductances. If you want to know more about these details and how to calculate these formulas, you just go to the eleneasy.com website. On that website, back in February, I have published an article on the inductors, and there I go into the calculation details to find these formulas. You'll find the link in the description in the video. And so now you have it. You have everything there is to know about inductors. What you have learned today is the foundation for using the inductors in simple to complex electronic circuits, from the design of oscillators to the one of filters. I hope you enjoyed this tutorial enough to give it a thumb up. Thumbs up are a way to improve the visibility of the video so others can find it more easily and can enjoy it too. Also, if you have not subscribed to the channel yet, please do so now to give me a help in making more and better videos. Talking about help, a small monetary contribution would also do it. There are a couple of options you can choose from: patreon.com and PayPal, both listed in the video description below. See you on the next video, and as usual, happy experiments!